Okay, shall we start?
Yes, sir.
Yeah, okay. So just let us try to quickly solve this problem. We had 5 kgs of liquid water at 30 degrees centigrade. We wanted to heat that up and make it into 5 kgs of water vapor. So we are going to heat. So if you want to write it in terms of block diagram, our we are going to supply this water. We are going to have a heater. We are going to supply heat from outside. That heat could be supplied by burning something, by combustion of a fuel, something like that. Don't worry about that just now. Okay, so we will not worry about how that heat is supplied just now. We will do those kinds of things in a while. But we want to make it into 5 kgs of water vapor. So if you think in terms of enthalpy versus temperature graph, so temperature versus enthalpy, obviously 5 kgs of water vapor at 120 degrees centigrade is going to have more enthalpy than 5 kgs of liquid water. So suppose I start here, so 30 degrees centigrade, and let's say in terms of the enthalpy, in enthalpy graph, I am I put my point somewhere here. So 5 kgs of liquid water. Okay, and I want to go to 120 degrees centigrade. Okay, obviously the enthalpy would be more. I'm so maybe I want to end up here. So this is 5 kgs of water vapor, right? So we want to go from this initial condition of 5 kgs of liquid water at 30 degrees centigrade, and we want to go to 5 kgs of water vapor at 30 at sorry at 120 degrees centigrade. So the point that I'm trying to make is that enthalpy is a state function, right? So instead of going by this red path, we can think about going by a different path. Let's say our intermediate temperature is 100 degrees centigrade, the boiling point of water at 1 atmosphere. So we might want to, rather than going by this red path, we might want to heat up liquid water from 30 degrees centigrade to 100 degrees centigrade. Then we might want to vaporize water from liquid water to 100 degrees centigrade water vapor, and then we might want to heat water vapor from 100 degrees centigrade to 120 degrees centigrade. So the first step, second step, and the third step, we can do this red operation going from this red path. We can do this in terms of 3 steps with this black curve or black path. So the stage 1 or step 1 is heating water from 30 degrees centigrade to 100 degrees centigrade. Then step 2 is vaporizing water, and step 3 is heating of water vapor, right? So we can call this as, let's say, point number 1 is our initial point. Point number 2 is our final point. And these intermediate path that we have taken, we can call this as point number 3. We can call this as point number 4. So the enthalpy change in going from 1 to 2 would be the same as enthalpy change in going from 1 to 3 plus enthalpy change in going from 3 to 4 plus enthalpy change in going from 4 to 2, right? So now the enthalpy change, please stop me if you have any doubt at any point of time. Okay, I'm just explaining a fairly straightforward problem. You did these kinds of things in your 11th standard, 12th standard. So now when we say enthalpy change for 1 to 3, this is a sensible heating. Now everybody understands what I mean by sensible heat. Sensible means there is a change of temperature. Latent means there is no change of temperature. The phase is changed from liquid water to water vapor. So sensible heating from 30 degrees centigrade to 100 degrees centigrade plus latent heat, liquid water at 100 degrees centigrade to water vapor at 100 degrees centigrade plus sensible heating again, but now this time it is sensible heating of water vapor from 100 degrees centigrade to 120 degrees centigrade, right? The first step 1 to 3 was sensible heating of liquid water. Okay, so what would be the sensible heating? That would be the mass of water into specific heat of liquid water into the change of temperature. Latent heat contribution would be mass of water multiplied by latent heat of water at 100 degrees centigrade. And the third step, sensible heating of water vapor, would be mass of water into specific heat of water vapor into the change of temperature, right? So the first step 1 to 3, mass of water is 5 kgs, Cp of liquid water is 1 kilocalories per kg Kelvin, change of temperature is 100 minus 30. So oops, so 100 minus 30 plus 5 times latent heat of water. So latent heat of water, if you just do Google, or we have done our wet bulb temperature. That time I gave you a formula, 540 plus 0.55 into 100 minus T. Now the temperature at which we want is 100. So this part just becomes 0. So this is 5 multiplied by 540 plus mass of water 5 kg, Cp of water vapor. So that is 0.45 into the temperature change 120 minus 100. Right, so just write the units for once. Kgs, 5 is in terms of kgs, Cp is in terms of kilocalories per kg per Kelvin change. This is your change in Kelvin. This is m. This is so mass in terms of kgs. Latent heat is in terms of kilocalories per kg. Mass in terms of kgs, Cp of water vapor in terms of kilocalories per kg Kelvin, and temperature change in terms of Kelvin. Right? So this Kelvin will go away, kg will go away. We will have units of kilocalories. We will have units of kilocalories. We will have units of kilocalories. All right. So this would be 5 times 1 into 70 plus 5 times 540 plus 5 times 0.45 into 1 into 20 degrees. Right? And then this answer would be in terms of kilocalories. Right? Any doubt so far? Can we go forward? And then you will get whatever your answer is. So let's not worry about what the answer is. Can we go forward? Anybody has any doubts? Now, next point that I want to make related to this problem is this. I had given you a formula when we had talked about wet bulb temperature. Lambda of vaporization was 540 plus 0.55 into 100 minus T, right? Let's see where this formula comes from. Any doubts so far? Anything we need to discuss? Yes, no? Can we go forward? Am I audible? Is the
Yes, sir.
connection
Yes,
still
sir.
there? Yeah, yeah,
Yes, sir.
the connection is still there. Okay. So let's try looking at this formula. Where does this come from? Again, if you construct a enthalpy versus temperature kind of curve, let's say we want to find out latent heat at T degrees centigrade, right? So suppose this is T degrees centigrade. Okay, so this is temperature. So now we want to convert 1 kg of liquid water from the liquid state, so liquid water, to water vapor. So this process, this step is nothing but lambda at T degrees centigrade. Do you agree with this? Yes, no?
Yes, sir.
Okay. What we do know is, we know the latent heat at 100 degrees centigrade, right? So we know the latent heat at 100 degrees centigrade. So we know that at 100 degrees centigrade, if I have liquid water and if I have water vapor, this temperature is 100 degrees centigrade. We know that this lambda is 540 kilocalories per kg, right? So if you want to traverse this black path, because enthalpy is a state function, instead of this black path, we can take this red path, that we convert liquid water from T degrees centigrade to 100 degrees centigrade. Then we vaporize water at 100 degrees centigrade, and then we cool water vapor from 100 degrees centigrade to T degrees centigrade. So the change of enthalpy in the black path, that is nothing but lambda at T degrees centigrade, would be the same as if we had traversed the path in steps 1, steps 2, and the step 3. So now we can write lambda at T degrees centigrade would be the enthalpy change for step 1 plus enthalpy change for step 2 plus enthalpy change for step 3. Right? And because we are looking at lambda, we are taking 1 kg of water. So enthalpy change for 1 kg of water would be 1 m into Cp into change of temperature for the step 1. We are heating from T degrees centigrade to 100 degrees centigrade. So this is 100 minus T plus enthalpy change for step 2, mass multiplied by lambda at 100 degrees centigrade, plus enthalpy change for step 3. We are cooling from 100 degrees centigrade to T degrees centigrade. So M into Cp of water vapor now. This first step is liquid water, and step 3 is water vapor. We are cooling from 100 degrees centigrade to T degrees centigrade. So T minus 100 if you want. And because we want to find latent heat, we have to just take mass as 1 kg, because latent heat we are representing in terms of per unit mass. So Cp of liquid water is 1 kilocalories per kg into 100 minus T plus 540 plus Cp of water vapor is 0.45 kilocalories per kg into T minus 100, or we can take the minus sign out here, we can subtract, and we can make it 100 minus T, right? And then this would be just 540 plus 1 minus 0.45, that's nothing but 0.55 into 100 minus T. So lambda at any temperature T degrees centigrade would be 540 plus 0.55 into 100 minus T, where T is in degrees centigrade. Right? Is that okay? Is that clear? Yes, no?
Yes, sir.
Yes.
Okay,
Yes,
so
sir.
try to draw these kinds of graphs, because it helps to visualize how we are doing the process, and we are taking help of the fact that enthalpy is a state function. So rather than traversing the black path, we could traverse the red path, or in this particular problem, instead of traversing the red path, we could traverse the black path. So if we want to think about doing this problem once again, we could have, instead of taking this blue path, we could have taken another path. We could have taken a path that we will vaporize liquid water at 30 degrees centigrade. So then we would have lambda at 30 degrees centigrade, and then we would heat up water vapor from 30 degrees centigrade to 120 degrees centigrade. So we could have vaporized and gone into water vapor at 30 degrees centigrade. Okay. And then heated up water vapor from 30 degrees centigrade to 120 degrees centigrade. Or we could have traversed another green path, where we could have heated liquid water from 30 degrees centigrade to 120 degrees centigrade, and we could have vaporized water from liquid state to the vapor state at 120 degrees centigrade. Right? We would have got the same answer. We would have exactly the same answer. Okay. Or if you don't like this blue path, if you don't like the black path, if you don't like the green path, you could have taken some other path. Let's say you could have taken this particular path. And ended up here. You could have taken this violet or lilac, whatever that color is. You could have taken this particular path, right? And you still have got the same answer. Only thing is, which path would you want to take? Black, green, blue, or this violet? Anybody?
So
Depends
one
on
which
what is
consumes
given.
the least amount of energy.
No, Hardik. All these paths are going to give you the same answer, because enthalpy is a state function.
Oh, okay, sir. Sorry.
So I suggest, Hardik, that so anybody wants this violet path? Yes, no?
No.
No,
No.
sir.
Why not? Because it's
Time
so
would
Sir,
much
be
more
too many steps
complicated.
involved.
So there are too many processes.
Too many processes, right? So Hardik or anybody, if you have a doubt that we've got this answer from the black path, okay, homework is you try this blue path or this green path. You would still get the same answer, provided you're taking lambda properly. Okay, let me just show you once. Let me just show you, Hardik. Are you
Yes,
convinced,
sir.
or should we solve?
No, sir, I'm convinced, sir.
Okay, but maybe other people are not convinced. Let's take this blue path. What is the blue path? Enthalpy change. Blue path. Enthalpy change would be vaporize water at 30 degrees centigrade and then heat water vapor from 30 degrees centigrade to 120 degrees centigrade. Let's quickly do that. Vaporize water at 30 degrees centigrade. So that would be mass multiplied by latent heat at 30 degrees centigrade. heating water vapor from 30 to 120 degrees centigrade. Mass multiplied by Cp of water vapor into 120 minus 30, right? So let's just do this very quickly. Mass, it is 5 kgs. Latent heat at 30 degrees centigrade. Now we are going to use this formula, right? It is 540 plus 0.55 into 100 minus 30, right? Plus mass 5 kgs, Cp of water vapor 0.45 kilocalories per kg Kelvin into 90. Hardik, just do this calculation and tell me what is your answer.
Yes, sir. 1 minute.
Sir, it is the same answer, 3095.
Thank you, Prathamesh. Hardik?
Yes, I'm doing it.
Yeah, okay. What takes so long? Just some multiplications.
Sir,
Yeah, Rishabh.
sir, this lambda T is equal to 540 plus 0.55, 100 minus T is the latent heat at T degrees Celsius.
Right.
Yes.
Yes, sir. It's the same, sir.
Haven't you used this formula for wet bulb temperature calculations?
Yes, sir.
This is the same formula, Rishabh.
Yes, sir.
Okay, or you had some other question, Rishabh?
No, sir, I was asking that only.
Okay. So Hardik 3095?
Yes, sir.
Yeah, same way. Same we had got 3095,
Yes, sir.
right? So are you convinced that all these paths would take the same energy because enthalpy, because enthalpy changes as enthalpy is a state function.
State function. Yes, sir.
So we might want to go this way, right? But only thing is it is too complicated to evaluate the enthalpy change in this weird kind of path. But we will still get the same answer provided you are able to analyze it properly, provided you are able to calculate it along this weird path. Okay, shall we go to the next problem?
Yes, sir.
Okay, so here is the next problem. We have been doing all kinds of condensation problems, right? So where we cool the air. So imagine that we have air, let's say ambient air. Let's say total pressure is, assume it is constant, 760 mm Hg. So we might want to use psychrometric charts. So ambient air, suppose the temperature is 45 degrees centigrade, percent RH is say 80%. We cool this water so that temperature becomes 20 degrees centigrade. Now obviously if this temperature is 20 degrees centigrade, if it is below the dew point, then liquid water will start condensing out. Do you agree? Yes, no?
Yes, sir.
Yes.
Right? And because it is cooling and water is condensing, let's assume that this liquid water also comes out at 20 degrees centigrade. And therefore, we can say that the air that is going out will have 100% relative humidity. It is completely saturated. Okay. So what I want you to do is take the basis as 1 kg of dry air coming into the cooler. So this cooler means I have to remove heat in order to cool, right? So I would like you to calculate the amount of heat to be removed. From the air entering the cooler per kg of incoming dry air. Shall we calculate now? Will you be able to calculate? Yes, no. Will you try?
Yes, sir.
Yes, sir.
Okay, problem is clear to everybody?
Yes.
Yes, sir.
Okay, we need some volunteers to solve the problem. Let's see who will be good volunteer. Those who have not volunteered at all, ever. Because I have not called on them. Prashasti, would you volunteer this time? Prashasti, are you there? She's not there. Anyway, I will have some more volunteers.
Sir, we have to use the ABC values, right? Which you gave in the previous
Good,
lecture.
good point, Praveen. Don't use the ABC values because the change of temperature is so small. It is just 45 degrees centigrade to 20 degrees centigrade, right? So the change of temperature is very small. You might want to use, so assume that CP of all components except water vapor, of course. Oh, I should just say why all components. I should just say CP of nitrogen and oxygen is just 7 by 2 R, like an ideal gas. Okay, but if you want, I can give you some CP values also. Right now, just use this value so that we don't have to worry about it. Okay, Praveen?
Yes, sir. And sir, R by 2 is 1 calorie, right?
R by 2?
Is 1 calorie.
I don't know.
Right.
Whatever
R by 2 joules.
units of R you want, you can take that unit of R. Units of R we have talked about long back. We have done so many ideal gas kinds of calculations where R was required. So whatever is your favorite unit of R, you can take. Who would like to volunteer? Of course, there is time. Let's see who would like to volunteer. Anybody would like to volunteer on their own? Rather than me calling out names. Mudit Nainani, are you there? See, he has left the meeting. As soon as I call out their name, people leave the meeting. I don't think it is a coincidence anymore. Don't be shy, don't be afraid. The only way you will learn the concepts is to solve problems. And there's no better way to solve than discuss. Mudit, are you there? Have you rejoined? No, he's not there. Mayur, are you there? Mayur Mule?
Yes, sir, I'm there.
Would you like to volunteer this time?
I'm not sure, sir, yet
Doesn't
whether
matter.
I'll.
Doesn't matter whether you are sure or not sure.
Sir, I need some time to solve.
You take your time. There's no hurry.
Okay, sir, I'll.
Great. Wonderful. That's the spirit. There's no hurry. You can take time. Only thing is I want somebody to discuss the solution so that discussion gets started. Otherwise,
Yes, sir,
I will
sure.
just keep on talking and I don't know whether anybody is listening or not. So first do the material balance. Material balance we have done plenty of times in these kinds of situations. So first do the material balance, take the basis as 1 kg of dry air, and then you think about doing the enthalpy balance. Okay, take 5-10 minutes. First do the material balance, find out how much liquid water condenses out.
So, but for
Yeah, I'm listening.
uh, yes, I'm just framing my doubt.
Okay.
So, but for each temperature, there will be different amount of water. So we need to devise an equation where the mass is changing with respect to change temperature, right?
Yes.
So, how would
Can
we do that?
we not take help of of the fact that enthalpy is a state function? Would it not help? That I don't care how much water condenses at each temperature. I know what is the total mass that has condensed out. Would it not help?
So I can't.
Okay, doesn't matter. You try. We will discuss all these issues. It's a good point that you have. So what I mean to say is that we don't care whether, as we cool from 45 degrees centigrade, we don't care how much water condenses at 44, 43, 42, 41, 40, 39, 38, 37. That is the path function, how much water is condensing at every temperature, every
Sir,
point.
we have to. Sir, we
Praveen,
have to
just let me
report.
complete. Let me just complete. Uh, so that's like a path function, how much water is condensing out at each temperature change as we go down from 45 to 20. But what we are interested is not how much water condenses out at each temperature, but what is the starting condition and what is the ending condition, what is the initial state and what is the exiting stage. Just like this problem, that's why I explained this problem in little bit more detail, right? We are not interested in how the, well, where did that go, how the water took the path from liquid water to water vapor, the red condition. We are not interested in that. We are only interested in the end condition 1 and 2, whether we go directly in a inclined line from 1 to 2, or whether we go from 1 to 3, 3 to 4, 4 to 5. Do you agree, Arya?
Yes.
So think peacefully. Yeah, Praveen, you were saying something.
Actually, sir, I just found a mistake. I'm
Okay,
making
you're
it
telling me
correct.
the answer. Oh,
Yes, sir, I just found a mistake.
okay, doesn't matter.
So 25.7 kilocalorie.
Okay, Atharva, answer and frequency. You're saying 25.7 kilocalories. Kilocalories, right?
Yes,
Right,
sir.
Atharva? Yeah.
Yes, sir. Kilocalories.
Hmm.
Sir,
Yeah.
sir, the CP value of the air will be 7 kilocalorie per kg per Kelvin, right?
CP value for oxygen, nitrogen, you can take as 7/2 R.
Sir, so it will be 7 kilocalorie per kg Kelvin, right?
7/2 R is 7/2 R. Whether it is 7, 9, 12, 40, I have no idea. It depends on what your units of R are. Is that okay, Praveen? You
Yes,
want me
sir.
to commit a value, and I'm not going to commit a value because it depends on what R you want to take. What set of units you want to work with. Is that okay?
Yes, sir.
So would change in pressure affect enthalpy?
A good point, Arya. Change in pressure does affect enthalpy, uh, but not at these temperatures. These temperatures are so small that change of enthalpy with pressure is not at these temperatures and not at these kinds of pressures, 1 atmosphere. For these kinds of substances, for some other substances, 1 atmosphere uh, is uh, is too large a pressure. So what I'm trying to say is that if we assume ideal gas, enthalpy is not dependent on change of pressure. Okay. This statement, I don't know whether you will agree with this statement or you will disagree
So,
with this
but
statement. This
so
statement.
we
Yeah,
are assuming a non-ideal case, right? Because we are compressing and it is liquefying in some
and it is
sense.
not compressing. We are having total pressure same 760 mmHg. So this
So,
pressure
but
is 760. This pressure is 760. This pressure is 760.
but I'm choosing a part where I am changing the pressure. So
Oh, you are choosing a path where you are changing the pressure. Um, yes. So if we assume ideal gas, enthalpy is not dependent on change of pressure. This statement you may or may not agree, but just wait till semester 3. We will actually prove that for an ideal gas, the enthalpy change is not dependent on change of pressure. Now, so that is one statement. Now, coming to your doubt, is enthalpy change dependent on pressure? Yes, enthalpy does depend on pressure if we are not having an ideal gas or if we are having a very large change in pressure. So for various substances, how to calculate effect of pressure on change enthalpy changes. For various substances, how do we actually calculate what would be the enthalpy change because of change in pressure? This again we are going to do in semester 3. Okay. Now that is second statement. Third statement is we are going to work with water at high temperature and high pressure. So what I'm trying to say is you don't have to worry about it till semester 3, but for this semester, we are going to look at water and water vapor at high temperature and pressure. So there we will have to worry about effect of pressure and effect of temperature for water and water vapor. and the enthalpy values for water and water vapor, meaning steam. So just another word for water vapor is steam. So the enthalpy values, how enthalpy change happens, or what is the enthalpy change for water and steam at high temperature and pressures, we need to worry about that in this semester itself. And these values we are going to take by something called as steam tables. Okay. So what steam tables are and how we use them, I will come to that in some time. There is also going to be a video that I will share with you that talks about steam tables and how do we use these steam tables. So this video also I will share probably in the next class, or maybe in the class after that. Okay, but so Arya, I have not answered your question. Right now, assume that enthalpy does not change with pressure.
Okay, sir.
I mean, that's a very short answer to your question, but I chose a little roundabout answer just to make you aware what is going to come in semester 3 and semester 4. So this course is really a starting point for what is going to come in semester 3. So don't neglect this course.
Sir, my answer is coming 27.89.
27.89.
Kilocalorie.
Yeah, okay. So shall we just say this is 25.7? Shall we just say this is 26? And your answer, shall we just say 29?
No, sir, then 28.
Oh, 28. 27.9. Oh, so 28. We might want to do just say around 27. How does it matter? Okay, anybody wants to have a break of 5 minutes can also have a break of 5 minutes. Mayur, are you ready with your solution?
Sir, just 3-4 minutes more.
Oh, okay. Take your time. Take 5 minutes more. Anybody
Okay,
who wants to have a break also can have a break. I will also go and have a glass of water.
Oh, so so I'm getting the answer as 26.47 kilocalorie.
26.47. So shall we just say all these are 20 around 27?
Yes, sir. I got 27.8.
Okay. Mayur, you can explain whenever you are done, whenever you are ready.
Sir, I don't have an answer, but may I tell my solution?
Yes, doesn't matter if you have an answer. If you don't have an answer, that is also okay.
Okay, sir.
Right, so everybody please note whatever I have said about enthalpy and enthalpy for changes for water and for other gases, effect of pressure. So just make a note. Okay, Mayur, so I will just let me put these things somewhere else. Right, so let me just move this out of our view. So that we have enough place to solve it. Is 7 by 2r. Okay, so Mayur, solution.
Sir, initial temperature is 45 degrees Celsius.
Yes.
So, and percent RH is 80. So from that, I calculated the vapor pressure using Antoine equation. Then the partial pressure.
Wait. So what are we doing is we are first doing material balance.
Yeah, material balance.
Right. I'm just trying to explain so that people who have some difficulties can also follow. So first we are doing material balance. Okay, so 45 degrees centigrade, you found out vapor pressure at 45 degrees centigrade. Can you tell me what is the value?
71.23 millimeter of Hg.
23 mm Hg. So if anybody is getting different value, just stop and shout out, right? Okay, now go ahead, Mayur.
Then by percent RH formula, I calculated partial pressure.
Would be 80% of 71.23. Okay.
Yes, which came out to be 56.984.
Okay, so shall we just say, okay, 56.98 mm Hg. Okay.
Yes. Just a minute. Then I calculated mole fraction of water vapor.
Right. Why do you want to calculate mole? Okay, okay, calculate mole fraction of water vapor.
Which came out to be 0.075.
Oh, wait. Why water vapor? Why is our mole fraction 0.075? Okay.
So mole fraction of dry air is 0.925. Just subtracting from 1.
Correct.
Sir, we already have 1 kg of dry air.
Right.
So we have 1 kg of dry air. So from this information, I calculated moles of water vapor and dry air, respectively.
So Mayur, can I just suggest something?
Yes, sir.
Just for your benefit, that if I take the basis as 1 kg of dry air.
Yes, sir.
Okay. Why not we just say I have 1 kg of dry air and we just write in terms of humidity? Or because CP is in terms of moles, you want to work in terms of moles? Is that right? I mean, is that what?
Yes, sir. I mean, that's the correct method, but I am always working with this method.
Moles. Okay, fine.
Yeah.
That is a good idea, Mayur. I fully agree. It is what everybody is comfortable with. So what you are saying is if I take 1 kg of dry air.
Yes, sir.
Then I have gram moles of dry air.
Which is 34.674.
Right. 1000 divided by 28.84. This is 30.
34.674.
34.674. So here you are saying incoming moles moles in the sense gram moles of dry air would be 34.674 and gram moles of water vapor would be
water vapor is 2.811.
okay, 2.811 gram moles.
Sir, I prefer this method.
No, absolutely fine, Mayur. I fully agree with you. It is just like some people like vanilla ice cream, some people like strawberry ice cream, some people like butterscotch ice cream, some people absolutely hate vanilla. It's absolutely fine. It is perfectly okay. I just wanted to say that you can do this as well because some people might prefer using humidity in terms of kgs of water vapor per kg of dry air. All right, now go ahead.
Sir, then we are cooling this air to 20 degrees Celsius.
Right.
But we don't know, some of that water vapor is converted into liquid water and remaining is staying in the vapor form itself.
Correct.
So I calculated again vapor pressure at 20 degrees Celsius.
Correct. How much is
partial pressure? That is 17.1895.
17.1895. Just try to round off. Don't fear rounding off. So 17.19. Okay.
Yeah, 17.19. And sir, partial pressure would be same as the vapor pressure as we are condensing out.
Right. So partial pressure would be 17.19 mmHg.
Yeah.
Okay, then you
so for an instance, sir, I assume that X moles of H2O gets condensed as liquid. Just for an instance.
Okay.
To make things clear, and then so water vapor moles of water vapor left would be 2.811 minus X.
Right.
But dry air would be same, 34.674 moles.
Right.
I already have partial pressure at 20 degrees Celsius.
Correct.
So I again calculated mole fraction at this 20 degrees Celsius.
Okay.
And
that is 17.19 divided by 760.
Yeah, 17.19 divided by 760, which comes out to be 0.0226.
Okay.
And I wrote the relation in terms of X for this
as well, right? So 2.811 minus X
divided by
2.811 minus X plus
34.674
minus is equal to 0.0226, and therefore
so I solved for X, which came out to be 2.01 moles.
2.01
moles.
Gram moles. Okay, so now that we have got X, wait, now that we have got X, let's write all these things so that we are clear what we are doing, right? It's always a good idea to write the values everywhere. So this X has come out to be 2.8, right?
2.01, sir.
Oh, sorry, 2.01. Right, now the air going out, dry air, gram moles is the same, 34.674, and gram moles of water vapor would be 2.811 minus 2.01, right? So that means it is 0.801, isn't it?
Yes, sir.
Okay. Now,
sir, let us do some energy balance now.
Now we will start, now that we have finished material balance, right?
Yes,
so
yes, sir.
If this problem is for 79 marks, we would have at least secured 39 marks. Now do energy balance. All right.
Sir, now we have two different processes, like H2O, initial H2O in the vapor form is going, some of it is going in liquid form and some of it is staying in vapor form itself, but the temperature is changing. So I think we need to do two different energy balances. One is for water and another is for dry air.
Okay, so let's do the enthalpy change calculations. for dry air?
Dry air. So we have 34.674. Okay, let us forget moles. We have 1000 kgs of dry air.
No, Mayur, you stick to your method.
No, but sir, in formula we need mass of air, no?
Acha, okay. So you are saying now enthalpy change for dry air, it is 1 kg of dry air. Okay.
1 kg of dry air, sir, which means we have, sir, I calculated the means weight of nitrogen as well as oxygen in this, so that we can do separate energy balance for them. So which came out to be 0.767 kg of nitrogen and
so this 1 kg of dry air, so 1
yes,
kg
contains
of dry air contains now
0.767 kgs of nitrogen.
Okay.
And 0.233 kgs of oxygen.
Okay.
So, sir, we can directly now calculate energy balance. We do not need to integrate this because you have given R as constant.
Okay.
That is 7R by 2, and in calories it comes out R value should be 2 into 10 raised to power minus 3.
Okay.
So which is 7 into 10 raised to 7 into 10 raised to minus 3. You can take it in kilocalories per Kelvin mole.
Okay.
So
what you are saying is R is 2 calories per gram mole Kelvin, or
yes, sir.
2 into 10 raised to minus 3 kilocalories per gram mole Kelvin. That
yes,
is what
sir.
Praveen was desperately trying to ask, and I was desperately trying to refuse answering. Okay.
Sir, now we can calculate energy for dry air, which is
so now enthalpy change for dry air.
Enthalpy change for dry air will be enthalpy change for nitrogen plus enthalpy change for oxygen.
Okay.
So
number of moles, 767 gram moles of nitrogen divided by 28 into 7 into 10 raised to minus 3, and enthalpy change is from 45 you are cooling to 20. Is that what you've done?
No, sir. Actually, here I did the mistake. I multiplied this with the mass of nitrogen. I forgot to convert it into moles. Sorry.
Right. So this is in terms of kgs. So, but CP is in terms of gram moles. Right. So either I convert the CP into kg, or I convert the kg into gram mole. Either way. So if
that is why I was getting some weird answer.
No, it doesn't matter, Mayur. It is perfectly okay. So if I convert this 767 into gram moles, it will be 767 divided by 28 molecular weight of nitrogen. Into
it is something
CP.
like 27.4 moles.
Okay. So I will tell you to calculate. So just let me explain. So gram moles of nitrogen into CP of nitrogen into the change of temperature. It is cooling from 45 to 20.
Yes.
And for oxygen, 233 grams divided by 32, that's the molecular weight of oxygen, into CP, 7 into 10 raised to minus 3 into 20 minus 45.
Yeah.
Okay, so now you calculate this number.
Just a minute, sir.
Excuse me, sir.
Yes, Ansh.
Yes, sir. Can we directly do 1000 divided by 28.84 for the moles, like combined?
Sure. Because CP is the same, right?
Yeah, that's why that.
Yeah, absolutely. Because this is the same. Had I given you different value for nitrogen and had I given you different value for oxygen, you could not have done that.
Yeah.
Actually, the values are slightly different for nitrogen and oxygen, but for the purpose of this problem, we are taking the same value.
Sir, it should be minus 6.067.
kilocalories. So just to
Kilocalories.
emphasize to everybody what this minus means, that I have to just remove the heat. I have to remove the heat because I'm too cool. Right? That means heat has to go out.
Sir, now we will do energy balance for water.
Right. So don't worry about whether that minus sign, why that minus sign has come. Okay. So now enthalpy change for water. Okay,
Sir,
now,
we have that 2.01 moles of water is going from vapor form to liquid form,
right.
and also changing its temperature from 45 degrees Celsius to 20 degrees Celsius.
Yes.
Sir, I calculated a latent heat of vaporization at 45 degrees Celsius.
Okay. So lambda at 45 degrees centigrade would be
which was 570.25.
540 plus 0.55 multiplied by 100 minus 45. This was 570.
0.25.
570.25 kilocalories per kg. Okay.
Yeah, and then my H2 is in all liquid form now. So I took it from 45 degrees Celsius to 20 degrees Celsius.
Okay.
So we will need, so the mass of 2.01 moles is.
So what you are saying is in terms of, yeah, so Mayur, just let me explain. So if what you are saying is in terms of enthalpy versus temperature, we had water vapor at 45 degrees centigrade. Some of this water vapor is going into liquid water at 20 degrees centigrade, and some of it is going into water vapor at 20 degrees centigrade. Isn't it?
Yes, sir. So first we are working only for 2.01 moles of water.
Right.
We are
So
just
enthalpy
keeping others
for,
on our side.
yeah, so enthalpy change for 2.01 gram moles of water.
Yes, sir, which is
right. So if we look at this part, instead of this black, what you are saying is you are converting everything into liquid water at 45 degrees centigrade.
Yes, sir.
Oops, I should draw the graph properly, otherwise people may object, because I have drawn positive temperature axis, so I should draw it properly. So I should say 45 is here and I should say 20 is here. So I have water vapor 2.811 gram moles. Part of this is going into liquid water at 20 degrees centigrade, and I'm only working about the initial or the only part that water is condensing, only about the 2.01 gram mole. So I have to convert the 2.01 gram mole of water vapor from 45 degrees centigrade to 20 degrees centigrade is of liquid water. Is that what you're saying, Mayur? And so
yes,
instead
sir.
of this red line, what you are doing is you are converting everything into liquid water at 45 degrees centigrade, and then you are cooling liquid water from 45 degrees centigrade to 20 degrees centigrade. Is that right?
Yes,
Is
sir.
that what you want to say? Ah, okay.
Yes, sir.
Okay.
So, sir,
okay.
First heat, that is just for converting, changing the phase.
Right. Step 1.
Yeah. So mass of that H2O is 0.03618 kg.
2.01 gram mole into molecular weight 18.
Yeah.
That will give me grams of water.
Yes, sir.
I will divide by 1000 to make it kgs of water.
Yes. Multiplied by 570.25.
Should I say 570.25 or minus 570.25?
Sir, so there won't be any discussion regarding plus or minus because you are not changing the temperature, right? You are just changing the
If I
phase.
wanted to heat up, if I wanted
Yes,
to
yes, sir,
vaporize,
yes, I got it. Got it, sir.
if I wanted to, because this has come, first part is negative, right? Enthalpy has to be removed. To convert water
Yes,
vapor
yes.
into liquid water, I have to remove enthalpy, right? So I have to put a minus sign,
Yes, sir,
right?
it should be minus. Yeah.
Okay, now liquid water is to be cooled from 45 to 20 degrees centigrade. So again, 2.01 into 18 divided by 1000, that will be kgs of liquid water into Cp of liquid water 1 into
1 into
20
change in
minus
temperature.
45.
Yeah.
20 minus 45. Isn't it?
Yes, sir.
Yes or no? So
Yes,
tell
sir.
me what is the value?
Just a minute, sir.
So calculate all this and tell me. Yeah. Take your time. Once you tell me, I'm going to tell you a simpler way. We are solving by your method. And after that, I will tell you a simpler way. Very simple.
Sir, it is minus 21.5361.
Yeah, 21.54 kilocalories.
Yes, sir. So now we are
Okay,
left
now-
with some remaining water vapor, which is directly going
Now enthalpy
into water
change.
vapor.
Correct. Now enthalpy change for
Remaining water
0.801
vapor.
gram moles.
Yeah, 0.801 gram moles.
0.801 gram moles. So that is nothing but 0.801 gram moles into 18 divided by 1000. So many kgs of water vapor into
Yes, sir.
0.45 specific heat of water vapor into 20 minus 45. It is cooling from 45 to 20. So tell me this value, Mayur.
Just a minute.
Yeah. I am also doing simultaneously.
Yes, sir. 0.162.
0.0162.
So 162. Just a minute.
Yeah, 0.162. Sorry. Yeah.
So now we will add up all the energy.
So heat total change of enthalpy
Yes, sir.
would be minus 6.067 plus minus 21.54 plus minus 0.162.
$27.769 minus 20.
Right? Or minus 27.8 if you like. So that's the change in enthalpy. This means heat to be removed is just 27.77 kilocalories. If I remove 27.77 kilocalories of heat, I will do this operation. Thank you, Mayur. Any other doubt?
No, sir.
Now, So I will perhaps tell you a different way of solving. Okay.
No, sir.
Yeah, Hadik. No doubt. Okay. Right. So look at this process. We will try to do this problem once again. We will do the whole problem. Just copy this. Let me just. Oops, 1 second. I think that OneNote just crashed. Just give me a minute. Just give me a second. Some problem with that OneNote. Just crashing. One second. Right. Anyway, if you want to see the recording, anyway, you will not be able to see this OneNote. Right. Okay. So do you recall I'm going to show you another method. Now, are you able to see the screen?
Yes, sir.
Yeah. So I'm going to tell you some other way of doing this problem. So do you remember our discussion on this potential energy? I could define potential energy of something with respect to some reference. If I take reference as the ground floor, I will have a certain energy associated with a pen. If I take reference as a floor of my house, I will have a certain potential energy. If I take reference as the first floor, I will have some other value of potential energy. So what we will do is we will try to solve this problem by defining reference conditions. And with respect to reference conditions, let's say this is my stream number 1, this is my stream number 2, and this is my stream number 3. With respect to reference, and some heat is to be removed, I will take this control volume. With respect to this reference condition, I will find enthalpy of stream number 1. I will find enthalpy of stream number 2. I will find enthalpy of stream number 3. Then across this control volume, we will simply write enthalpy balance as enthalpy coming in must be equal to enthalpy going out, just like I did material balance. Enthalpy coming in is because of stream 1. Enthalpy going out is enthalpy going out in stream number 2. Enthalpy going out in stream number 3 plus some enthalpy that is removed in order to do this cooling operation. I'm cooling, so I have to remove that enthalpy. Heat I have to remove, or enthalpy I have to remove, right? So if I write this enthalpy balance, then enthalpy that I need to remove, or heat that I need to remove, would just be enthalpy from stream number 1, enthalpy of stream number 1 minus, that is what comes in, minus what goes out from stream number 2 and 3, enthalpy of stream number 2 and minus enthalpy of stream number 3. Right? If I write this, this is just the same way as we have been writing our material balances. Do you agree with that? Right, and we will solve this problem in detail, and we'll make sure that we get the same answer. So now all I have to do is define a reference condition, and with respect to that reference condition, I will just find enthalpy of stream number 1, enthalpy of stream number 2, enthalpy of stream number 3. So let me say I can take any reference condition I want. This is our choice. I will say reference that I want is, let's say, 20 degrees centigrade. Air have set at 20 degrees centigrade. We set enthalpy of air to be 0. We set enthalpy of liquid water to be 0. This is our choice. Okay. In a minute, it will become clear why I took 20 degrees centigrade. But can I set enthalpy at this reference condition of whatever components I want? So these air and water are the components, and I have to also specify the state, because some component could be in the liquid state, some component could be in the gas state. So I am setting for my own convenience, I am setting that at 20 degrees centigrade, enthalpy of liquid water is 0, enthalpy of air is 0. So when I say air,
Sir, this here is ambient, right?
when I say air, I will say the nitrogen and oxygen, the dry air part of it. The dry air part of it. Praveen, is that okay?
Okay, sir.
Okay, Mayur, we are going to need some more values from you because I don't remember those values now. I have rubbed them all out.
Okay, sir.
So I will ask you for values whenever I need it.
Yes, sir.
So this is what we are going to say. We are going to say our reference, and at that reference, whatever components are there in the problem and whatever is the state of their of those components, we are going to say that some of these these components in their some respective state have 0 enthalpy. Now I just have to work out what is the enthalpy of stream number 1, stream number 2, stream number 3 with respect to this reference, right? So let's work out what is the enthalpy of stream number 1 with respect to this reference. Okay, let's work that out. So enthalpy of stream number 1. So again, if I write the enthalpy versus temperature graph, so now temperature is 20 degrees centigrade or 45 degrees centigrade. Now we are setting a value 0, just like we set potential energy to 0, either on the ground floor or on the floor of our house. Now we are going to write values on the axis of this enthalpy. We are going to say at 20 degrees centigrade, nitrogen in the gas state, oxygen in the gas state, and liquid water have 0 enthalpy. Now what is this? What does the stream 1 contain? Stream 1 contains nitrogen, oxygen, and water vapor. So if I work out the change in enthalpy, in going from reference to 45 degrees centigrade, this would be nothing but enthalpy at 45 degrees centigrade minus enthalpy at reference condition, which is 0. Okay, so whatever is the enthalpy change in going from the reference condition to the condition of 45 degrees centigrade, and these components in their respective whatever the state they are in this particular stream number 1, that change, if I work out, that would be nothing but enthalpy of stream number 1. Do we agree with this? Do you disagree with this? Yes, no? Anybody agrees? Anybody disagrees? All I'm saying is enthalpy
Sir,
change.
can you repeat it once?
I am saying enthalpy change. Let's say this is point number 4 and point number 5. I don't want to take 1, 2, 3. Well, let's say point number A and point number B. What is the enthalpy change from A to B? That is the same as enthalpy at B minus enthalpy at A. Do you agree with this? Enthalpy is a
Yes,
state
sir.
function.
Yes, sir.
What is the enthalpy at A?
0.
0.
0.
0.
So enthalpy at B is the same as enthalpy change in going from A to B. What is enthalpy of B? Enthalpy at B. Enthalpy at B is nothing but enthalpy of stream number 1. Do you agree? With respect to the potential energy, I had something on the ground floor. With respect to that, what is the potential energy of 1 kg of that pen? That is nothing but potential energy of that pen, because I have defined with respect to some reference. Do you agree with that? That's why we talked about potential energy last time. That's why I had asked you to see the recording. Do you agree with this statement?
Yes, sir.
Yes, sir.
Okay. So now what is the enthalpy change in going from A to B? What is at A? It is nitrogen at 20 degrees centigrade. I have to take it to 45 degrees centigrade. So moles of nitrogen into Cp of nitrogen into 45 minus 20 plus moles of oxygen into Cp of oxygen into 45 minus 20. But there is a third component in stream number 1, water vapor. Right now, if you look at the water vapor, in state A, I have liquid water. In state B, I have water vapor. So I could take liquid water, I could heat it up to 45 degrees centigrade, and then I could vaporize that liquid water. Right? So then kgs of liquid water into Cp of liquid water into 45 minus 20 plus kgs of liquid water into latent heat at 45 degrees centigrade. Do you agree with this? This would be the enthalpy of stream number 1. Do we agree with this? Anybody has any doubts? Somebody say something.
So it's clear, sir.
It is clear to one person.
So please
Yes, sir.
explain it again.
Yeah, Arya. So enthalpy change in going from A to B. What is going from A to B? Nitrogen is going from A to B.
Yes, sir.
Oxygen is going from A to B.
Yes, sir.
Liquid water is at A, that is going to B. Because I have defined my reference as liquid water, I have made enthalpy of liquid water to be 0. Do you agree with that?
Yes, sir.
Now this is okay?
Yes, sir.
Yeah, so Mayur, moles of what nitrogen, how many moles of nitrogen were there, Mayur? I forgot.
27.4.
27.4. Cp of nitrogen was 7 into 10 raised to minus 3 into 25 plus moles of oxygen. How many were there? How many moles of oxygen were there?
7.274.
7.274 into Cp, 7 into 10 raised to minus 3 into 25. How many kgs of liquid water was there in stream number 1? Or how many kgs of water was there, water vapor was there in stream number 1? We had some 0.28, some 2.811 gram moles, right?
Yeah, 2.811. So kgs would be 0.05.
Yeah, no, it doesn't matter. Let's write 2.811 into 18 divided by 1000.
Okay.
Those many kgs of liquid water into Cp of liquid water 1 into 25 plus 2.811 into 18 divided by 1000. And what was the latent heat at 45 degrees centigrade? 570 something, 575. You had some number?
570.25.
Okay, 570.25. Somebody calculate this number. Arya, you can calculate.
Sir,
Yeah.
sir, why are we taking latent heat at 45 degrees Celsius?
We are going by this path from A to B. We are going by this path, path 1 and path 2. We could have gone by this path also. We could have vaporized everything at 20 and heated up water vapor from 20 to 25. Or we could have gone from 20 to 100. We could have vaporized and cooled from 100 to 45. It is up to us, Rishabh.
Yes, sir.
So
Arya.
I got 53.9.
53.9.
Sorry, sir. Wait. I'm yet to do.
Yes, sir. Same answer.
Thank you, Rishikesh. We'll just wait for Arya to confirm.
Yes, sir. Same answer.
Thank you. Now let's work out enthalpy of stream number 2. What is there in stream number 2? 2.81 gram moles. So sorry, not 2.81, 2.01. Mayur, 2.01, right? Yeah. So what is
Yes,
the
sir.
enthalpy of stream number 2? How do you calculate that? If I calculate enthalpy change for stream number 2 to be taken from reference to conditions of stream 2, that enthalpy change would be enthalpy of stream 2 minus enthalpy at reference conditions. And this is nothing but 0. Right? So enthalpy of stream number 2 would be enthalpy change to take 0.201 sorry, 2.01, not 0.201. Mayur, you should stop me if I write something wrong. Enthalpy change to take 2.01 gram moles
Sir, I have a doubt, sir.
Wait, Praveen, let me complete. Enthalpy change to take 2.01 gram moles of liquid water from reference condition to 20 degrees centigrade. Somebody can tell me this? What is our reference? What is our reference? Reference is 20 degrees centigrade, liquid water having 0 enthalpy. What is in stream number 2? Stream number 2 is 20 degrees centigrade liquid water. So what is the enthalpy of stream number 2? Is it not just 0?
Sir, 0.
0.
Mayur, do you agree?
Yes,
Arya,
sir.
do you agree? Praveen, do you agree?
Yes, sir.
Yes, sir.
So now do you see why I took 20 degrees centigrade as reference? I don't have to bother about stream number 2 because stream number 2 has 0 enthalpy. Because it is already there in the liquid state. Now enthalpy of stream number 3. What is enthalpy of stream number 3?
0.
Enthalpy of stream number 3 is 0. What is there in stream number 3? Nitrogen at 20 degrees centigrade, oxygen at 20 degrees centigrade, but stream number 3 has water vapor at 20 degrees centigrade. Do you agree?
Yes, sir.
Who was saying 0?
So sorry, by mistake, sir.
No, doesn't matter. Uru, So enthalpy of stream number 3. What does stream number 3 contain? It contains nitrogen, it contains oxygen, it contains water vapor at 0 degrees centigrade. Sorry, at 20 degrees centigrade, not 20 degrees centigrade. Right? Nitrogen at 20 degrees centigrade has 0 enthalpy. Oxygen at 20 degrees centigrade has 0 enthalpy, because we have made it 0 by choosing our reference. But we have water vapor at 20 degrees centigrade, whereas our reference is liquid water at 20 degrees centigrade. Right? And water vapor we have 0.801 gram moles. So enthalpy of stream number 3 would just be the change in enthalpy of taking 0.801 gram moles of water from 20 degrees centigrade in the liquid state to vapor state. Do you agree with this? So this would be 0.801 into 18 divided by 1000, so many kgs, multiplied by latent heat at 20 degrees centigrade. Again, think in terms of enthalpy versus temperature. 20 degrees centigrade, liquid water has 0 enthalpy. I want to take it to vapor state, because in stream number 3 it is in the vapor state. So this is nothing but lambda at 20 degrees centigrade. And how many moles I have to take? 0.801. 0.801 into 18 divided by 1000, those many kgs. Now latent heat at 20 degrees centigrade. It is 540 plus 0.55 into 100 minus 20. Somebody calculate this number. Arya, can you calculate?
8.42.
Yeah, 540. Let me just calculate.
Yes, sir.
Just
8.42.
8.42 kilocalories. So now let's go back to our energy balance. What was our energy balance? Heat to be removed, enthalpy coming in from stream number 1 would be equal to enthalpy going out. Enthalpy is going out in stream number 2, stream number 3, and whatever enthalpy I have removed from that air. So enthalpy removed or heat removed would be enthalpy coming in from stream number 1 minus enthalpy going out from stream number 2 minus enthalpy going out from stream number 3. So stream number 1, what was the enthalpy coming in? 36.186 minus enthalpy going out in stream number 2, 0. Enthalpy going out in stream number 3, 8.42. What is the value?
Sir, same answer, 27.76.
Thank you, Mayur. Do you agree? So either you can do Mayur's way, absolutely okay, or you can do this way. This way is a better, easier way to do, because you don't have to keep on tracking what has changed from what to what. You don't have to keep on tracking. You have to just worry about the conditions of 1, conditions of 2, conditions of 3. Arya, does that answer your question? You had asked at what temperature, what is condensing, how much is condensing at what temperature?
Yes, sir.
We don't have to worry about that, because enthalpy is a state function. all I have to worry about is enthalpy of what comes in, enthalpy what goes out with respect to some reference.
So actually the problem that I was facing was that I was keeping the state dynamic, as in
Yeah, and I understood what you're trying to do, but that's what I'm trying to say, that you don't have to worry about it because enthalpy is a state function. I have to only worry about the control volume over which I'm applying the enthalpy balance. And then I have to only worry about what comes in and what goes out, not how it goes from in to out.
okay, sir, but still it's difficult for me to visualize.
So visualize it like this: enthalpy of stream number 1, enthalpy of stream number 2 with respect to reference, just like we are saying potential energy. That's why I had asked you, please look at the recorded lecture. Please look at the recorded lecture. Let me explain again. This is the room. I have a desk here. I have a 1 kg pen here. I want to take this pen from here to here. This is 1 meter. This is 3 meters. What is the change in enthalpy or change in potential energy now? It is mass of the pen 1 kg into g into 3 minus 1. Isn't it? Arya?
Yes, sir.
Or if you want, you can take that 1 kg pen from here to 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 here. That is your path. That is your dynamic state. But if you think about this as a control volume, I am taking my pen from location 1 to location 2. If I say that I stay on the 2nd floor, this is my ground floor. I will define potential energy with respect to the ground floor. What is the potential energy of pen at 1? It is mass of the pen 1 kg into g into the height of the pen with respect to ground floor. Suppose you are staying on the 2nd floor. This height is say 10 meters, or 3rd floor. This height is say 10 meters. What is the potential energy of pen at 1? It is the same as change of potential energy, or if I write change of potential energy in taking pen from ground to your desk. This would be 1 kg into g into 11 meters. This would be the same as potential energy at location 1 minus potential energy at ground floor. Isn't it? Potential energy at ground floor we have defined as 0. So potential energy of pen at location 1 is nothing but the change in taking it from ground to this. So 1 into g into 11. Same way, what is the potential energy of pen at location 2? It is potential energy change in taking it from ground floor, 0 potential, 0 energy, to the energy at potential energy at the top of the cupboard. It is 1 multiplied by g into height 10 plus whatever was the height. I think it was 3 meters. Right? 10 plus 3, 13 meters. So now what is the change of potential energy? going from 1 to 2? It is nothing but
1 into
potential
G
energy
into 2.
at 2 minus potential energy at 1. So this is 1 into G into 13 minus 1 into G into 11, which is same as 1 into G into 2. So whether I do this or whether I do this, do you agree?
Yes, sir.
So don't worry, even if things are not clear, I will leave you with one more problem. So homework. And then maybe things would be a little bit more clearer. Okay, so here is a problem. So this is a homework problem. So imagine that there is a dryer. So we have wet particles. Let's say these particles are, there is some P, product P, and there is water. P is our product, particles, and water. W is water. Okay. So let's say this contains, it is 20% by weight is the water. So that means if I write in terms of weight percent, it is 20 and 80. Okay. And let's say these particles are coming into this dryer at the rate of 30,000 kg per hour. Total, it's a continuous dryer, kg per hour. It is 30,000. Okay. So these particles are going to get dried. In order to make them dry, we are supplying hot air. Okay. So let's say hot air is 100,000 kg per hour at 200 degrees centigrade. Assume that this air is bone dry, so there is no water vapor. Okay. These particles will get dried. So P would be there and W, water, would be there. In terms of weight percent, I want it to dry to 99 weight percent and 1 weight percent water. Right? You can write in terms of kg per hour. Obviously the P would remain the same in terms of kg per hour. There's no P going out here. What is going to happen to the air now?
It will cool down.
Right, air will cool down and become more humid, isn't it? Yes, no?
Yes, sir.
Yeah. So let's assume that these wet particles are coming in at 30 degrees centigrade. These particles also get heated up slightly. So these particles are at 40 degrees centigrade. Right. So this air will get cooler, meaning its temperature will be less than 200 now. And it will get more humidified because it will have now water vapor. Some of the liquid water has vaporized into water vapor. Right? Do you agree? Is the problem description clear to everybody?
Yes, sir.
Is the situation
sir.
clear to everybody?
Yes, sir.
Yes. what I would want you to find out, assume that this dryer is adiabatic, meaning no other heat is coming in or going out, right? Whatever heat is being supplied is because of this hot air. No other form of heat is entering or leaving the dryer except the hot air part of it, right? I would like you to calculate the temperature of this air, and I would also like you to calculate what is the percent RH of this air, right? We can assume that total pressure is 760 mmHg throughout all cases. So let's give some numbers. Let's call this as stream number 1. Let's call this as stream number 2. Let's call this as stream number 3. Let's call this as stream number 4. Right? So just to emphasize, stream number 1 has this product P. It has water in the liquid form. Stream number 2 has only hot air. No water vapor is coming in stream number 2. Stream number 3 has this product P and liquid water. And stream number 3 is at 45 degrees centigrade. Stream number 3 has 99 weight percent P, 1 weight percent water. Stream number 4 has air which is lesser than 200 degrees centigrade, because it has to transfer heat to vaporize the water from stream number 1, and that whatever is the water that is vaporized will go along with the air in stream number 4. So stream number 4 is a slightly cooler but more humid air. Slightly in the sense you have to work out what the temperature of that outgoing air 4 in stream number 4 is, and what is the percent RH of stream number 4. Okay, let me give you some CP values. So CP values for P, let's assume that CP value for P, where is that value gone? Yeah, CP value for P is, let's say, 0.25 kilocalories per kg Kelvin. CP value for air let's assume that it is 0.24 kilocalories per kg Kelvin. So don't worry about the ABC values and all that. Just take this value 0.24 per kg of air. CP value for water vapor, we can take it as 0.45 kilocalories per kg Kelvin. CP for liquid water, we can take it as 1 kilocalorie per kg Kelvin. Latent heat at any temperature T degrees centigrade is 540 for water plus 0.55 into 100 minus T. Okay. Is the physical situation clear to everybody?
Yes, sir.
What is to be found is clear?
Yes, sir.
Yes, sir.
Okay, and CP values, you can take these CP values. Don't bother about that integration and all that. Okay, it's not worth the effort. The concept is more important, right? Either you can do by Mayur's method, or you can do by my method. My in the sense, we define a reference, component, state, enthalpy. We say that at reference temperature, air in the gas state has 0 enthalpy, water in the liquid state has 0 enthalpy. I can take any state, any reference temperature I want. One convenient temperature would be 30 degrees centigrade, and I will say P in the solid state has 0 enthalpy. The advantage of defining this reference is enthalpy of stream number 1. Stream number 1 is at 30 degrees centigrade. It has P in the solid state. It has W in the liquid state. No air. So this would automatically imply that enthalpy of stream number 1 is just 0. Do you agree with this? Yes, no?
Yes, sir.
Only Praveen is agreeing with me.
Yes,
Nobody
sir.
else.
Yes, sir.
Arya. 2, 3 people have agreed with me. Mayur.
Yes, sir. Agreed.
Agreed. 4. Right? You take this as a reference. Mayur, you solve it by both methods, by your method also and by this method also. And make sure that
Okay,
you
sir.
get the same answer.
Yes, sir.
Sir, one question I have.
Yes.
Sir, the stream 3 and stream 4 will have same temperature, right?
Stream 3 and stream 4 need not be. It need not be. It need not be. I have never told you that heat transfer is complete, that they have reached thermal equilibrium. I have never made such statements. Air going out can be at a different temperature. Solids, dried solids going out can be at a different temperature. Praveen, is that okay?
Okay, sir.
But you had some other doubt. I mean, why
No,
were
sir,
you
the
saying that they
previous.
should be at the same temperature?
No, sir, they were going out from the same.
They are going out. If I allow thermal equilibrium to be reached in the dryer, then yes, they would be at a same temperature. But I need not. I can have a very short dryer where the time required to reach equilibrium is not sufficient.
Okay, sir.
So solve by Mayur's method and solve by reference by defining reference. Just to help you, I have already defined the reference for you, 30 degrees centigrade. And these conditions. Component, state. With respect to this reference, you can find enthalpy of stream number 1, 2, 3, 4. Stream number 1 just happened to be 0 because that is the same as our reference condition. So then we will write enthalpy balance. Enthalpy in must be equal to enthalpy out. Enthalpy in is because of stream 1 plus enthalpy in is because of stream 2. Enthalpy out is because of stream 3 and enthalpy out is because of stream 4. Right? This is the energy balance that we are going to write. Why? Because we have been writing material balance also in the same way, and material coming in, material going out. That's why we are defining a reference, and with respect to this reference, we are calculating what is the enthalpy of stream 1, stream 2, stream 3, stream 4, and then we write enthalpy balance. Okay, so try both methods. It may take you some hours to do this, but okay, it is perfectly all right to take several hours to do this. If you take several hours for one problem, next problem, let's say you take 3 hours for solving this problem, next problem you will take 2 hours, next problem you will take 1 hour, next problem you will take 30 minutes, next problem you will take 5 minutes. Okay. learning is exponential. Okay, shall we stop for the day?
Sir, actually, I had a doubt in the previous question, so should
Yeah.
I ask it now or
Which
later?
previous question? No, which previous question? Ask,
The
ask,
one
ask.
before this, which we solved in class today.
Mayur wala, huh?
Yeah, yeah.
Huh.
Yeah, so in this, I took the dew, I calculated the dew point temperature first.
Huh.
So, and then I divided the whole water stream into two parts, like the one which
Huh.
condenses out and one which goes.
Huh.
Yeah, so when you solved in both the methods, we never considered the dew point. Is it because we consider only the final state and initial
Correct.
state?
Enthalpy is a state function. I don't care what the dew point is, as long as I have inherently used the dew point in calculating that 2.811 grams come in and 2.01 gram moles of water condense out, and 2.801 gram moles remain in the vapor state, right? The dew point is
Yes.
automatically considered. It is dew point is about 20 degrees centigrade. That's why it is getting condensed.
Yeah, yeah.
Okay.
No, but
So
when if I use the method of dew point, then
you
I'll
can
have
use
to
any method.
calculate. Yeah, then
You
I'll
can
have to calculate lambda at that point, at
you
dew
can
point, right?
use any method you like, as long as you are consistent in, as long as you draw this enthalpy versus temperature chart and think about what is going from where to where at what condition. So for example, instead of going from liquid water to water vapor in this manner, you might want to go to some intermediate temperature and vaporize and heat. Enthalpy is a state function. Whether I take this black path, whether I take the dotted line, whether I take the red path, whether I take the blue path, go up to 100 degrees centigrade. Punch, is that okay?
Yes, sir. The only thing which
You
I was asking is when if we consider the dew point thing, we'll have to calculate lambda at the dew point, right? Because then it
no,
will start.
no, it depends on what path you are taking. Whether you are taking the black path, then you have to worry about lambda at 45, or you are taking the blue or the dotted path, then you have to worry about lambda at 20, or you take the blue path, then you have to worry about lambda at 100, or you take the dew point path. Let's say dew point is 30 degrees centigrade, then you take the lambda at 30 degrees centigrade. It is your path that you have to worry about.
Yes, yes. Got it.
All right.
Yeah, yeah.
Enthalpy is a state function. You choose the path and calculate accordingly, but be consistent with what your path is. That's why I'm telling you, draw the path for yourself. Don't do it mentally. Once you draw the path, then only you will be consistent in your calculation. Bookkeeping, it is just a matter of bookkeeping. All right.
Yes,
Will
sir.
you be able to do this homework now?
Yes, sir.
Arya, can we meet sometime on Saturday?
So Saturday, yes. Sir, I'll let you know because there is some reshuffling of lectures.
All right.
So I'll let you know. Yeah.
Sure, because we can solve. Didn't take, if we take an extra session on Saturday, we can solve this problem in more detail and carefully and slowly and answer doubts whatever people may have. Okay, but first solve the problem before Saturday.
Sure, sir.
Okay, so let me stop recording.